Okay, so this talk is about Cocoon, which is a new programming language and a verifier for software-defined networks that enables SDN verification at scale. So to motivate this work, let's start with a running example. So here we would like to design and verify a software-defined campus network. The network consists of multiple IP subnets. We would like communication within a subnet to proceed unrestricted, whereas packets sent across subnets are filtered by the network's access control policy. So physically, this network topology consists of operational zones that are connected to the core network via routers. Zones represent, for example, buildings on the campus, and so we allow the same subnet to span across multiple zones, and we allow the same zone to host multiple subnets. For access control purposes, we associate a router with every zone, and we require that all packets leaving or with every subnet, and we require that all packets leaving or entering the subnet are inspected by its corresponding router. So, for example, if you wanted to send a packet from the red subnet to the green subnet within the same zone, it would have to traverse the red and the green routers first. Next, we define Ethernet switching topology and forwarding rules for each zone. And finally, we do the same for the core network. Putting it all together, we get our network architecture. So this kind of controller can be built in any language of your choice. And what it does is basically it monitors network topology and the user-defined configuration and generates a set of open flow tables for every switch in the network. Now, if we wanted to verify whether the controller works correctly, there are a couple of options we could go with. And one of the options is to use one of several excellent data plane verification tools that have been developed recently, which basically extract the network configuration and use some form of symbolic reasoning to check whether this configuration has some desired properties like loop freedom or pairwise reachability. So these techniques actually scale really well. But one issue you have with them is that this style of verification is applied after the network has been deployed in production, at which point fixing a bug can take a while and may lead to significant downtime. Which is why another option is controller verification. So instead of verifying an instant snapshot of the network, we verify the program that generated the snapshot, which guarantees that any possible network configuration produced by the controller is correct. This is an undecidable problem of software verification in the general case, but there is some recent work that shows that by restricting the language in which you write the controller, the problem can be made tractable for some classes of applications. Still, the scalability of these techniques is still not as good as we would like it to be. And then both approaches share a common limitation that by verifying against properties, you can find bugs, but it's very hard to guarantee correctness in this way, because there may always be additional properties that we care about that the network violates. And so one twist in this story is techniques that instead of doing property verification, verify the network against a specification. So we have a complete specification of desired externally visible behavior, for example, written as a big switch abstraction, and we want to verify that the actual network configuration behaves equivalent in some sense to this spec. Again, it's a computationally harder problem than property-based verification, and at least in our experience, it doesn't yet scale as well. So ideally, we would like our network verifier to be scalable. We would like it to be able to verify network statically before it's deployed. And it should be exhaustive. It shouldn't miss any bugs. And with existing approaches, you can get 1 out of 3 at best. OK, so let's go back to our running example and see if we can find some inspiration there. So one thing I want to point out is that this example has a whole lot of structure. And it's the kind of structure we should be able to exploit to speed up verification. So we start with this high-level spec, which basically talks about what the network should do as opposed to how it does it. So it abstracts away all the details of the actual topology and forwarding logic, and only talks about end-to-end behavior. And then from there, we go in a sequence of stepwise refinements, where every refinement fills in some of the details missing at a higher level. And importantly, these refinements are modular in the sense that every refinement focuses on one part of the network, pretty much ignoring everything else. So this structure is not unique to this particular case study. In fact, I would argue that any real network is amenable to this kind of hierarchical modular decomposition. So for example, in one of our case studies, we looked at a wide area network connecting multiple data centers. And that can be naturally decomposed into the global fabric and local fabric within each data center, which can then further be divided into the core layer of switches and top-of-rack switches. In yet another case study, we looked at a virtual network, which naturally decomposes into the physical fabric and the virtual fabric built on top. So we did not implement a cellular network, but if we had implemented it, we would probably decompose it into the edge layer consisting of base stations, the core of the network, and the internet gateway layer. So this kind of modular decomposition is key to compositional verification. So we can beat the state explosion problem by verifying each refinement, one refinement at a time, as opposed to the whole thing in one go. And that's exactly what Cocoon is about. So Cocoon is really three related things. It's a new SDN design method based on this concept of stepwise refinement. It's a programming language that supports this method by making refinements a first-class entity in the language, and it's a verifier for the language. And altogether, they achieve scalable, static, and exhaustive verification. So all the three properties we care about. So network design in Cocoon starts with a high-level specification from which you go through a sequence of refinements, verifying each refinement as you go, until you reach the level of detail where we specify exactly the behavior of each switch, and so we can go and compile that into flow tables for each network switch. Refinements are transitive, which means that the final implementation is guaranteed to satisfy the spec, which really means that any configuration produced by this SDN application at runtime will satisfy the specification. So let me walk you through a few lines of Cocoon code just to give you a feel for the language. So this is the Cocoon program for the top-level specification in a running example. So as every Cocoon program, it consists of roles, where a role specifies a set of similar network entities. It could be pretty much anything. It could be, for example, top-of-rack switches, or routers, or in this case, the main role in the specification is the output port of an end host of the network. Roles are parameterized, with every instantiation of parameter corresponding to a concrete instance of the roles. In this case, our parameter is the IP address of the host. Clearly, not all possible IP addresses exist on the network, and so each role also has a guard condition which specifies a set of its instances. So here we assume that there is a chost function, which stands for the characteristic function of the set of hosts, which takes an IP address and returns true if this address exists on the network. Now, the body of the role is basically an imperative program that takes a network packet as implicit argument. It can modify the packet and send it to one or more other roles. So here we start with applying the security policy to the packet. We say that if the source address and the destination address of the packet are on the same subnet, then we don't need to do anything. Otherwise, and we assume here that there is this IP to subnet function that takes IP address and returns subnet identifier, for example, by looking at the net mask. So if they're not on the same subnet, then we use the ACL function that encapsulates the current security policy of the network to filter out illegal packets. So next, we drop packets that are being sent to invalid destination. And finally, we send the packet to the input port of the destination host. Now, the send operator, it's a powerful abstraction mechanism in Cocoon. It abstracts away the actual topology and how the packet actually traverses the network. And it says that at this high level of specification, we just want to say that the packet will eventually be delivered to the right destination address. And it's up to subsequent refinements to specify exactly how that happens. So this is actually a complete spec for this simple example. But what's the deal with all these functions that are used here? So you may have noticed that when I was explaining the design of this network to you, I never told you exactly how many hosts there are, how many subnets, what the exact topology, or what the exact access control policy here. Because none of these things are relevant for understanding the design. And nor should they be relevant for verifying it. In fact, they can change at runtime. Right? Whenever a new host enters the network or a link fails, these parameters can change. So what we really want to do is we would like to verify the network for any possible instantiation of these parameters. So to do this, Cocoon supports this concept of runtime defined functions. So these are basically uninterpreted functions which are declared in the Cocoon program, but their definition only is only given at runtime. So the aim is to verify to verify refinements for any instantiation of these functions, except that while we may not care about their exact definition, we might care about some properties that have to hold for them. So for example, we don't care exactly how many IP subnets there are in our system, but what we do care about is that given a valid IP address, this IP to subnet function should map it into a valid network address. And so to formalize those assumptions, we have a special construct in Cocoon called assume. So roles are also the main unit of refinement in this language. So we refine the spec by removing one of the roles and replacing it by a more detailed implementation, potentially decomposing it into multiple roles. So in this case, for example, our first refinement takes the host out role and provides a new definition for it. So we now introduce routers into the network. And so instead of saying the packet gets delivered directly to the destination host, we say that the packet gets delivered to the input port of the router, and then router is a new role defined in this specification. So Cocoon naturally decomposes the program into the static part, which consists of refinements and assumptions, and the runtime part, which is represented by the RDFs. And so the verification process is also two-phase. We statically verify refinements, assuming that assumptions hold, and then all we have to do at runtime is, given a concrete instantiation of RDFs, we have to check that they actually satisfy those assumptions. Which brings me to the mandatory architectural diagram of Cocoon. So there are three components to it. There is a static verifier that checks refinements before the network is actually deployed. There is an assumption checker that collects RDF definitions from multiple sources. They can come, for example, from automated network management tools or directly from administrator, or they can come from the underlying SDN controller that monitors network topology and notifies the Cocoon up whenever configuration changes. And then finally, if all refinements are satisfied, then the Cocoon compiler, it combines the lowest level specification with the RDS we are given and outputs flow tables for all switches. And at the moment, we support OpenFlow and P4 switches. So I'm only going to say a few words about how the verifier actually works. So there's more in the paper. Effectively, we formalize roles as functions that take a packet and non-deterministically returns a set of packets. So for example, a unicast role will return one packet, whereas multicast role returns many. And then refinement is just a subset relation, which says that for any input packet, the refined role R head can only generate an output if this output is also allowed by the abstract role R. So we can exactly reduce the amount of, we cannot increase the amount of non-determinism in the specification by doing the refinement. We then encode this problem as a model checking problem and verify the refinement using the Corral model checker. For runtime assumption checking, we simply encode our properties in SMT and we use the Z3 solver to check the assumptions. So we implemented and verified a range of different network designs using Cocoon. So the goal was really to show that it's a general methodology that's applicable to different kinds of networks. And so you can see that our case studies range from wide area networks to virtual networks, enterprise networks, data center topologies, and internet exchange point. So let's look at some of the results from these experiments. So the first thing I want to point out is that in all cases, we were able to specify network behavior, including all the refinements, in only a few hundred lines of code. More importantly, the size of the top-level specification was very, very small in all cases, under 100 lines of code, and usually much less than that. The reason it's important is because Cocoon verifies that this complex implementation of the network is a refinement of the high-level spec, and the high-level spec is what we have to trust. So it better be simple and concise. So depending on the structure and the complexity of the network, it took between 1 and 6 refinements to get from the abstract spec to the implementation. So compositional verification was very efficient. We were able to verify all of these designs in only a few seconds. And this is largely due to the fact that we do verification compositionally. So to show this, we what we did is we lumped together all the refinements into one big refinement step and tried to verify it in one go, as shown below. And as you can see, in some cases, it became intractable. So next, we look at the efficiency of runtime phase of verification. So this is the time that it takes Cocoon to verify assumptions at runtime. So the baseline, so this experiments we did on one of our case study, which was essentially a realistic version of the running example. We used netcut as the bottom line because netcut is pretty much the only other available tool that can do that can verify against specification as opposed to do property-based verification. So the blue line here shows how long it took netcut to verify the entire data plane configuration, and the red, the time that it took netcut to verify the data plane configuration, and the red line is the time it took Cocoon to only check assumptions. And as you can see, it's exponentially faster because Cocoon did all of the heavy lifting offline using all the structural information available to it. And then the final set of experiments relates Cocoon to all this data plane verification tool. So Cocoon is all about checking that the network implementation correctly refines the high-level spec. So what if we don't trust the spec? What if we still wanted to check that our network has the simple properties we expect, like pairwise reachability? Well, one thing we could do is we could apply these tools like HSA or Veriflow to the resulting data plane configuration. However, we can do better than that. We already know, Cocoon already proved for us that this configuration is a refinement of the specification. Instead of verifying the concrete data plane, we can verify the abstract specification. And this should be much faster because it's abstract and has smaller state space. And indeed, it is much faster. So for the same case study, we verified pairwise reachability using HSA on the concrete configuration. That's the green line. And then we did the same on the abstract spec. And that's the red line. And you can see it's 2 orders of magnitude faster. So what do we learn from all this? So this concept of stepwise refinements, it's actually not new. People have studied it for many years in software verification, and it never became mainstream there. Because it turns out that writing software by refinement is actually pretty hard. So the lesson learned from this work is that for networks, on the other hand, it's a very natural and practical methodology. So in particular, networks allow concise, high-level specifications. Module boundaries in networks are much cleaner in software. As a result, we can much more easily and naturally decompose them into this series of refinements. And finally, once we have done this decomposition, we are able to efficiently verify those refinement steps using automatic tools. So I think that going forward, this is really the right way to build and verify networks. Thank you.
Questions? So I have a question. So you showed that your tool can significantly reduce the verification time. I wonder how to think about the benefit for developers in terms of the time the operators actually use, because operators need to refine their configuration many rounds. Do you have any comments on that?
Sure. So we only have completely informal evaluations. So we never did, real developer studies. But I think that actually one of the nice things about Cocoon is it also gives you a very nice language for programming these things. At least this has been our experience.
So I have another question, which is what are the potential configurations that may be hard for you to specify and refine?
Right. So a data plane that does some sort of complex computation, for example, we would never be able to verify cryptography in the data plane. At which point you basically get to this generic problem of software verification, which can be undecidable.
Okay, thank you.